Bismillahirrahmanirrahim. Dear students, this is Inorganic Material Chemistry, Chem 3115, and this is third lecture on hydrothermal synthesis. This is last lecture of this course, and after that we will revise some specific topics. So the key concepts of this lecture includes new trends in solvothermal crystal growth processes. We will discuss some examples, for example, some oxides and non-oxide materials synthesized by hydrothermal or solvothermal method. We will also discuss some nanomaterials, and then we will talk about some examples of specific materials which have been synthesized by using hydrothermal method. And after that we will talk about applications like advantages and disadvantages of hydrothermal methods. So talking about new trends in solvothermal crystal growth processes, we can use hydrothermal or solvothermal process for growing large single crystals. There are two different domains. One are crystal growth of oxides and the second one crystal growth of non-oxides. Here are some examples. Alpha quartz, it shows piezoelectric properties. Just like alpha quartz, some other oxides like aluminium phosphate, gallium phosphate, barium arsenate, they also show alpha quartz like piezoelectric properties. They can be synthesized by using hydrothermal method. Calcite, which shows optical properties, it can be synthesized with wide spectral range over a wide spectral range. Zinc oxide is a semiconducting material, wide band gap, transparent dielectric and piezoelectric properties shows. Similarly, crystalline aluminosilicates containing pores and cavities of molecular used as absorbent catalysts as ion exchange materials can be synthesized by using hydrothermal methods. Some other oxides like KTP, calcium, titanium, oxygen, phosphorus oxide, similarly calcium, phosphorus oxide and hydroxide, lanthanum phosphoroxide, and some other materials which are given here, they can be synthesized by using hydrothermal method and especially the zeolites. These are some figures which are showing single crystals of diamond on the upper left side, then the quartz, piezoelectric crystals, they are made by hydrothermal method. So we can see the single crystal of diamond and the crystals of quartz which are in different shapes. These single crystals can be synthesized by using a simple hydrothermal method, and these crystals are very transparent, very fine crystals of large size. Similarly, the large single crystals of non-oxides can be synthesized. During last years, strong efforts have been done for controlling the solvothermal crystal growth of gallium nitride using a process which is derived for alpha quartz or zinc oxide crystal growth. The reference is also given here. This is the name of the article, and it has been published in Journal of Crystal Growth 2007. Now gallium nitride is a non-oxide material. Oxygen is not present in this material. Such efforts are supported by the existing or potential applications of gallium nitride. What are the potential applications? It is used in optoelectronics, high frequency, high power electronics, and fast speed communication devices. So, this material can be synthesized by using hydrothermal method, simple hydrothermal method. The third one is the crystal growth of materials as nanoparticles. We have discussed too much about introduction of nanotechnology or introduction of nanomaterials, and where we have discussed about their potential activities and properties, enhanced properties, all kind of properties. So as the size is reduced to the nanometer range, the material exhibits specific properties due to quantization effects. In such a case, the morphology plays an important role. Nanomaterials can be synthesized in zero dimension, one dimensional, two dimensional, even three dimensional. Nanomaterials can be synthesized. Three dimensionals are actually clusters of nanomaterials. So usually we do not consider them. We only consider zero dimensional, one dimensional, and two dimensional nanomaterials. Zero dimensional nanomaterials are those materials in which no dimension is out of nanoscale. One dimensional nanomaterials are those in which the one dimension is not of nanoscale while other two dimensions are of nanoscale. Two dimensional nanomaterials are those materials in which two dimensions are not in nanoscale while one dimension is in nanoscale. So recently one dimensional nanostructures, wires, rods, tubes, they have been the focus of intensive research owing to their applications in mesoscopic physics and fabrication of nanoscale devices. The formation of a one-dimensional nanostructure depends on two steps. The first one is the nucleation and the second one is the crystal growth. In addition, for generating nanostructures, three main parameters must be controlled. So to control nucleation and crystal growth, these three parameters are very important. The dimensions of the nanostructures, the morphology of the nanostructures, and monodispersity or uniformity, that the particles are uniform throughout their structure. The atoms are equally distributed. Dimensions we have just discussed, zero dimensional, one dimensional, or two dimensional nanomaterials. There can be so many morphologies, like they can be in the form of wires, rods, in the form of tubes, discs, cones, balls, spheres. So there can be different morphologies of the nanostructured materials which can be synthesized by using solvothermal or hydrothermal process. These are schematic illustrations of the different strategies for achieving one-dimensional growth. For example, in figure A, we can use the anisotropic structure. In figure B, confinement by a liquid droplet in the liquid solid process. In figure C, we can use certain template and we can grow certain material on the template. In figure D, we can use just like the use of capping agents which are able to modify the growth rate in the direction And figure E is the self assembly of zero dimensional nanostructures, and figure F is the size reduction of one dimensional microstructures. They can be converted into nanostructures. The reference is also given here. The article has been published in Advanced Materials in 2003. So these are different uh, strategies which can be used to grow one dimensional, and all of this can be done by using solvothermal or hydrothermal method. Now we will discuss some examples like synthesis and characterization of cadmium selenide. We will focus only on synthesis, not on the characterization. The synthesis of cadmium selenide and the synthesis of cadmium selenide zinc sulfide. It is a composite material in which two different kind of materials are mixed and they have been synthesized. Cadmium selenide or zinc sulfide both are non-oxide materials. These materials does not contain oxygen. So first of all, the synthesis of cadmium selenide. This is the whole procedure for the synthesis of cadmium selenide. You can see these are the starting materials. We have metal cations in solution, just like 3.08 gram of cadmium nitrate. It contains cadmium ions. These are metal cations. In hydrothermal method, the precursor material is very important because we need to use such kind of precursor material which can easily be dissolved into water or some other aqueous solvent. On the next, we have 0.86 gram of sodium selenide. It will give us selenide anions. So it also contains metal atoms in the solution. What are the metal atoms? Sodium metal atoms. They are mixed and we get cluster formation of cadmium selenide. We are using hydrazine and sodium hydroxide. Then all of the reactants are added into an autoclave and they are heated at 180 degrees Celsius temperature for 2 or 3 days, and finally we get the product which is shown here, the powder product of cadmium selenide. Next is the synthesis of cadmium selenide and zinc sulfide. So for cadmium selenide, the reactants are cadmium nitrate with 4 water molecules and sodium selenide. While for the synthesis of cadmium selenide and zinc sulfide, the reactants are cadmium nitrate, sodium selenide, and also zinc nitrate, and we have ethyl nitride sulfide. So first of all, for the synthesis of cadmium selenide, as just discussed before, we have cadmium and selenide. They are dissolved into a solvent. On the other hand, for the synthesis of zinc sulfide, zinc cations and sulfide ions, they are dissolved in solvents separately and after that they are mixed. Now we have two solutions, one containing cluster of cadmium selenide and the second containing zinc sulfide clusters. And we want to synthesize cadmium selenide and zinc sulfide, a composite material. Sometimes the formula can be shown just like cadmium selenide at the rate of zinc sulfide. It means that one of the material has been encapsulated by the other material. So zinc sulfide is making the outer sphere and cadmium sulfide is present inside the zinc sulfide. So both of the solutions, they are mixed together. L-cysteine is used here along with water as a solvent, and similarly the temperature is 180 degrees Celsius, and the reactants are placed in an autoclave, and the autoclave is heated at 180 degrees Celsius for a certain time of period, and we get cadmium selenide, zinc sulfide uh, composite material. Now there are some characteristics of hydrothermal synthesis, like some advantages of hydrothermal or solvothermal synthesis, and some disadvantages of hydrothermal or solvothermal synthesis. Talking about advantages of hydrothermal or solvothermal synthesis, number one is most materials can be made soluble in proper solvent by heating and pressuring the system close to its critical point. Critical point we have discussed in first lecture. It is the point where the solvent is half of the solvent is in liquid phase and half is in gaseous phase. So the first advantage is that most of the materials, they can be easily dissolved in a proper solvent by using hydrothermal method. The second one is the significant improvement in the chemical activity of the reactant, the possibility to replace the solid state synthesis, and materials which may not be obtained via solid state reaction may be prepared by using hydrothermal or solvothermal synthesis method. The third one is products of intermediate state, metastable state, and specific phase may be easily produced. Novel compounds of metastable state and other specific condensed state may be synthesized. Number four, this method is very easy and precise. This method can be used to control the size of the particles, the shape, distribution like morphology, crystallinity of the final product, and this can be done by adjusting the parameters such as reaction temperature, reaction time, solvent type, surfactant type. It is often used for the synthesis of nanostructured materials. The surfactant just helps to grow the materials in nano size. Also the precursor type, these are different parameters which can be controlled to control the size, shape and crystallinity of the final products. Substances which are low in melting points, high in vapor pressures and tend to go pyrolysis will be obtained. So this method can be used to treat with such kind of substances which have low melting points and they are high in vapor pressure, and they can easily broken down by using a high temperature like in solid state method. So here we are using a closed container and we are increasing the temperature of the container slowly, and after that when the reaction is complete, the reaction container is cooled down to the room temperature very slowly. So during this process the material which has been grown inside the container will be safe and will not undergo pyrolysis. Next are the disadvantages of hydrothermal or solvothermal synthesis. The main and biggest disadvantage is the need of expensive autoclaves. These are very simple autoclaves which I have shown you in previous lectures as in examples. So as if we want to synthesize more complex materials, then we need more complex autoclaves, and which are very expensive. In simple solid state method, a simple co-precipitation method, we are just using simple beakers and simple apparatus. But when we use hydrothermal method, we need very expensive autoclaves, and which is difficult to arrange sometime. The second one are the safety issues during the reaction process. Because we are dealing with very high pressure and very high temperature. Temperature is not very high, but the pressure is very high, so it is possible that the autoclave can be broken down, or it can have leakage, and it can destroy our reactants, and finally we may not get a product. So the safety issue is also very important. The third one is that the chemical reaction is occurring in a box which is closed, and we cannot see anything inside the box, and we have just placed it into furnace or into an oven. We cannot observe what are the chemical reactions or chemical changes which are occurring during our synthesis process. So it is just like a black box. So we do not have access to the black box, and we cannot observe any change, any color change, any physical state change occurring into the reactants when they are converted to the products. So this is also a very big drawback or disadvantage of this method, that the physical changes which are or chemical changes which are occurring, they cannot be observed by naked eye, which can be observed in co-precipitation method. Then here are some applications of hydrothermal synthesis in the preparation of nanomaterials. The hydrothermal method has been firstly proposed to simulate the genetic condition of geological minerals. Later it has been adopted in the synthesis of molecular sieves, porous materials, and for the crystal growth. At present, by using different starting materials, different solvents, and by adjusting reaction temperatures, as well as other experimental parameters which we have discussed in previous slides, the different researchers, they have reported the synthesis of various kind of nanostructures through hydrothermal or solvothermal approaches, including metal oxides, carbonaceous nanostructures, and other materials extra. Hydrothermal or solvothermal method can be used for the synthesis of zeolites, which are a big class of compounds. There are so many zeolites which have been prepared, and they have a lot of potential properties. Hydrothermal method can also be used for the synthesis of simple metal oxides. It can be used for the synthesis of carbonaceous materials, nanowires, and the conditions can be changed during the hydrothermal method or during the synthesis through the hydrothermal method. Dear students, this is all about hydrothermal synthesis. There are some conclusions that are to open a route through new soft chemical process. Hydrothermal process is also called soft chemical process, kinetically controlled for stabilizing metastable systems. This method helps the synthesis of specific structures using templates to control the nucleation crystal growth process for the preparation of nanocrystallites well defined in size and morphology. This method facilitates through the improvement of the chemical reactivity and the development of mild temperature conditions, the synthesis of hybrid nanosystems. Mass production of samples can be carried out by using hydrothermal synthesis method. So all the objectives of hydrothermal are solvothermal process. They require to be optimized. For example, the physiochemical properties of precursors, the physiochemical properties of the solvent, and the thermodynamical parameters like pressure and temperature. So to carry out a chemical reaction through hydrothermal method, we must need to optimize these conditions. Solvothermal processes appear to be important in the near future, not only for developing basic sciences but also for the development of new industrial processes in mild conditions of temperature and pressure. This is all about this lecture and all about hydrothermal synthesis. Thank you very much.